With that, we're going to kick off with an overview of the state of carbon removal solutions, and I'm going to hand it over to Amishi to walk us through. So Amishi, please take it away.
Hi everyone, can you hear me? Yeah, awesome. As mentioned, my name is Mishi, and I just wanted to open first with a big and sincere thank you. It means a lot that you guys registered and are attending today, and we really appreciate that you guys came here. I've worked in carbon management space for a while now. I've been at the DOE and was there when CDR was just starting to come to the forefront. And it's been amazing how much it's taken off and how much that community has been established. And I love it. I just think it uses a lot of jargon, right? Like I said, CDR, I should have said carbon dioxide removal. It's got a lot of terms in it. So sometimes it can feel alienating. But the thing is, CDR isn't crazy complicated. That complexity, that nuance that we feel, it comes from the fact that there's just a lot of approaches that come under this umbrella term of CDR. So it's great that we have a ton of shots on goal, but it's also important for us to distinguish all of these shots from one another because each pathway has its own set of benefits and compromises. So today I just wanted to do a little technical walkthrough because I'm a scientist and that's really what I like to do if I have some people. But it also gives us some context before we dive into the panel, which I'm really, really pumped for. So thanks again, and let's start from the beginning. Climate change. I will not give too much about climate change because I don't have time. So I'm going to have this working assumption that we all think CO2 is a bummer and we got to do something about it. So there's a couple things that we can do, right? Carbon avoidance projects. That's what you have seen a lot of in this voluntary carbon market space. A carbon avoidance credit is a credit that represents 1 ton of CO2 that would have otherwise been emitted from a project emitted without a project activity. So this is kind of like a renewable energy project, avoiding the emissions from a fossil fuel plant. Then you have this other type of project, carbon removals projects. And a removal credit represents 1 ton of CO2 that's been removed from the atmosphere and our ocean and durably stored because of a project activity. These projects aren't tied to a point source of emissions like a power plant or a landfill or an industrial facilities. These projects are targeting these legacy emissions in our atmosphere that have built up and diffused into our oceans. They're removing that carbon dioxide and taking them out from play. We'll dig into these carbon removal pathways throughout the presentation and in the panel. So I really like this slide, mostly because it shows a really nice step back view of the complexities that you have in your CDR pathways. And there's a distinct set of benefits and compromises that come with each pathway. A great place to start if you want to dig into any one of these technologies is the CDR primer. Maybe a step up is RMI's Applied Innovation Roadmap, which is a little bit more of a technical document, goes over like 30 plus approaches, but we adapted this graphic from the UN report because we could center it around a couple core themes: the capture mechanism and the storage medium. I think if you distill CDR down, capture and storage are the key scientific aspects that drive cost and durability. Cost and durability drive financial risk. Every stakeholder in the CDR community has to deal with financial risk. Generally speaking, less complicated capture, less durable storage means less cost. That's this left side of the graph, and I'll dig into a couple of those. More complicated capture, more durable storage mediums means more cost. And that's more on the right side of this graph. And I'll dig into a couple of those as well. So as you can tell, we've got like 4 things we got to dig into, and we'll try to fly through this technical walkthrough. The first is nature-based removals. This is the one that most people have comfort with. It's actually covered by others on the science team. Another reason I'm going to breeze through it. But the most common type of project you'll see is ARR, or afforestation and reforestation. The graphic in the middle is a little technical walkthrough of what a typical process is. You'll have degraded land or barren land, and you will plant some trees. In terms of afforestation, it means establishing new trees and new tree forest cover in an area where trees or forests didn't exist. Reforestation is replanting trees on recently deforested lands. From a carbon perspective, Both afforestation and reforestation store that carbon in that neat biomass. So that's step three. That's that new and or restored forest system that's photosynthetically drawing down carbon dioxide, storing it in the biomass, and as well as in the soil carbon. The main benefit here is that that biological capture mechanism, it's the most cost effective and the most scalable way to remove CO2, period. The main challenge, though, is the fact that this deployment relies on a really vast open system. So the drawback is monitoring, reporting, and verification. MRV. That's another umbrella term that you'll hear me say often. It's a group of activities, right? That's all about tracking that carbon dioxide. You want to, if you're paying for it, you want to make sure that the carbon that you're paying for is quantified right. You want to make sure it's monitored and stays there, and you want to verify that. So all of these activities that track that carbon dioxide fall under this term of MRV, generally speaking. So MRV in a system like this, big open forest system, ends up being harder. Next, we'll go to another biological capture process that I call bikers. So it's biomass carbon removal and storage. I like this graphic. I know it's a little busy, but it's versatile. So bikers, right? Pathway is another umbrella term. You're gonna pick up that I'm using a lot of umbrella terms, but it's really helpful, right? It's all the things you can do with biomass, which is a ton of different things. On the left side, you're starting with this initial carbon drawdown, the same thing that you had with your nature-based solutions. It's cheap, easy, boom, you get your carbon locked away. Then you need to source sustainable biomass. Keyword there being sustainable. This can be residues from forest management, agricultural debris. It can also be municipal solid waste. That's that little truck coming from the city. We tried to cover all these little options. So it's all these organic waste that didn't really have any other value or use. They're then processed in something we're calling like the conversion facility, right? That's step number three. It's this one facility that you are converting the biomass into something else. It can be a ton of different technologies that you deploy here. It can be pyrolysis, heating with that oxygen, combustion, that would be heating with oxygen, hydrothermal liquefaction, fermentation, gasification, a ton of different things. But regardless of whatever you do, you're going to have your products fall into one of these three categories. First is you can have CO2 or your bioproduct go to dedicated geologic storage. That's a high durability trap, right? Like, say if you're doing combustion in that facility, you could capture that CO2 off that smokestack and put it underground. If you were doing pyrolysis and getting a bio-oil fraction, you could put that in geologic storage as well. The second category is bioproducts for disposal or application. So say if you were doing pyrolysis again, you can have a biochar fraction. You could apply that to a field. If you had biomass and you dried it, compressed it, cased it, you had a little bio brick, you could throw that into a landfill and that could be a disposal. That's another option. And our final option is this catch-all. It kind of says other co-products. Sometimes with biomass projects, you aren't just looking at the carbon value, you're also pulling other values out of that biomass, right? If you're combusting it, you could be using that heat to generate electricity. If you were fermenting in your facility, you could be creating ethanol. So there are other products that you could be generating from your biker's facility or your conversion process. Similar to ARR, it's highly feasible. It's photosynthetic. We have biomass available. The sustainability aspect is something you need to dig into and make sure you're sourcing well, but it's still scalable and feasible. The MRV also is a little bit easier than ARR. In the middle right there, we have that facility. It's a lot more constrained and defined. So MRV is a lot more easier to execute in Biker's process compared to ARR. But the trade-off is a higher cost. You're having a lot more steps that involve people, you're procuring biomass, you're processing it, you're transporting it, sometimes even paying for that final fate of the bioproduct. All those add to the cost. And that's the trade-off that you'll have, your benefits and your compromises. If we switch gears and we talk about a different type of capture mechanism, right? A geochemical one, we can come to things like enhanced rock weathering. I really like this idea that rocks, I'm a geologist. you'll get that vibe. This idea that rocks affect climate isn't new. Ramo et al., which was an awesome female geologist in 1992, had a pivotal Nature paper. It was like the Himalayas affect climate, and you're like, what? We were putting all these rocks up into the atmosphere. They were weathering down. They were actually drawing down CO2. So for enhanced rock weathering, we're doing that just like on a much smaller scale, and we have to do it so much faster. So when we say ERW, there's a couple steps that we got to take. We got to process our rocks. You know, you got to get the right rocks. Don't let anyone tell you all rocks are created equal. Some have the right cations that you need. You need iron, magnesium, calcium, whatever it may be. But you got to take those rocks and you got to process them into the appropriate specifications. Fancy way of being like, we just need rock dust. The smaller it is, the faster it can react. So you get your rock dust and then you spread it on a field, usually a cropland, some areas that you have characterized, because you want to know the soil that it's engaging with, right? So if you've characterized your farmlands, that's really helpful. And then the next step is this rainfall. Rainfall like has a little bit of CO2 absorbed into it in the form of carbonic acid. It's that taste that you get if you've ever drank rainwater before. So that rainwater that's a little acidic will hit your tiny rocks on the surface of your fields, and that's where you get your weathering reaction going on. And your rock will actually weather away into its components, its ions. And that carbonic acid, that carbon that was in the rainwater, gets locked up as a bicarbonate ion. So those are the little red circles that we have throughout this graph. That buffered runoff really will follow the fate of water. Some will go into the water table, some will go into streams, rivers, valleys, oceans, right? So that will be the ultimate fate of that locked away bicarbonate that you have. There's a couple big benefits that I really like about ERW. Like this idea of spreading something onto a field isn't really new for agriculture. They have confidence, they have capabilities to do so. But the drawback, again, is the openness of the system, right? We're talking about really big natural processes. We're talking about rainfall over fields. We're talking about rivers. We're talking about ocean dynamics. All of that adds up to a more complicated and more costly monitoring, reporting, and verification in MRV regime. And finally, my other favorite is direct air capture. We worked on this a lot. This has been an area that the carbon management space has been super excited about. And it's a really interesting engineered concept, right? And it's pretty simple. So you'll have an air contactor as your first step. So that's number one. Air contactors, if they're active, will have big fans. And the idea is you want a lot of air to come through because you want your CO2 molecules to contact a capture medium. A capture medium can be a solvent, liquid, a sorbent, kind of like a sponge, or it could be like a membrane, kind of like a filter, and you want it to hold on to your CO2 molecule. Now that you've captured your CO2 molecule, your medium is loaded, you want it to let go of that CO2, right? You spent a lot of time engineering this really complicated medium. So you'll have to give it some kind of resource. You're going to have to give it heat or electrons or temperature or pressure or a vacuum, something to swing off that CO2 molecule and reuse that medium. So after you do that, you can get this pure stream of CO2 that you can compress and transport. And you have a couple of options when you're looking at a CDR system, right? You can send it to a durable product, like curing it in concrete or a synthetic ag, or you can inject it underground for geologic storage. Both are really high durability options for that CO2 that you've created and come out with. So what are we doing when we're investing in CDR right now? Like, what does the market look like? We've talked about these projects, and the market right now is really dominated by these advanced market commitments or offtakes, people being like, I'll pay you for the credits that you generate mostly into the future. And it's this investment into this singular project. So you're investing in these particular dots. So you've concentrated your investment into that set of benefits and that set of compromises. So if I was you, what CDR would you invest in? According to this graph, you would want to invest in the upper left corner. And there's nothing there. There's really not a lot of durable and affordable projects. That technology isn't there. So what you're seeing are these like buy regimes, right? Some people are investing in durable but expensive projects. These ones like DAC and direct air capture and direct ocean capture, really trying to move the market towards growth and towards commercial scale in the hopes that they come down a cost curve. You have other folks that are investing in temporary and affordable solutions, right? They're looking to make an impact now. And that's in this lower left corner where you have ARR projects. And then you have a new kind of group of folks that are thinking about these temporary removals, but also have a premium associated with them because they have a co-benefit. Perhaps it's biodiversity or something, or water, where they're willing to pay that premium because this temporary removal credit has something else attached to it beyond just a carbon value. It's still a really nuanced question, but Rubicon has a different approach as well. We are building carbon credit portfolios. We demonstrated it before. There's no singular carbon project that hits every single quadrant, hits every single goal. So by combining all of these projects or a spectrum of these projects into a single investment, such as our Rubicon Carbon Ton, we can balance this diversity of benefits and compromises into a singular high impact investment that can meet immediate demands. This is just like an illustrative graphic, really, but you can kind of see that there's 4 technologies that are blended into this portfolio, which balances the risks and hedges the costs across them. This portfolio is also actively managed over time. So over the decades, you can see the portfolio's composition will change depending on how technologies mature and how they come down price curves and cost curves. So active management means that buyers aren't locked into this singular technology at the point of investment at current prices. We have a white paper that's coming out, and we'll talk about this in a lot more detail because I can't do it justice in 10 minutes. So I would definitely stay tuned for that. But I think it's really important to see a visual and talk through it because I spent a lot of time today, and I will likely, like tout like emerging technologies. I think they're great, but it's also good to have this idea that, some of them may not be like the cost curve of technology number 2. They won't come down dramatically. Some of them might be technology 1 or technology 3, where the cost curves don't come down quick enough or they don't scale enough. That's why we need an all of the above approach whenever we're talking about avoidance or we're talking about removals, because it's really important for us to not conflate these two. Low durability does not mean low integrity. You can have a high integrity solution, a high climate impact decision through diversification. I'm pretty sure I have hit my 10 minutes, and I really just want to say thank you. And I'm so pumped for the panel. So thank you guys, and let's go. Back to you, Margaret.